Hello, this is Shuzhen Sun. Welcome to my presentation. Today, my topic is statistical yield analysis for defect-tolerant VLSI circuits. The problem I'm talking about is a chip fabrication, and yield here means the percentage of good chips versus the total number of fabricated chips. So the yield can be from 0 to 100%. The defects are the physical anomaly that can kill a circuit. Defects can certainly reduce the yield because defects can lead to open circuits, short circuits, and can impact the device operation. But we can use some statistical yield models to predict the yield depending on the average number of defects. The number is the number of defects averaged. The simplest model is Poisson's model. Poisson's model assumes the defects are spatially uncorrelated points. And every defect can result in a circuit failure. The Poisson's model can be derived from binomial distribution because if we divide the chip into n sub-areas, then because they are statistically independent, then each sub-area having one fault, the probability would be lambda divided by n. We let k be a random variable that represents the number of faults occur on this chip, then k would satisfy the binomial distribution. If we let n goes to infinity, then the binomial distribution would become the Poisson's distribution. And the Poisson's yield model is simply when k equal to 0, then the probability would become the yield. It will be e to the power of minus lambda, a very simple formula. But the reality is, each fabrication, the number of defects can be different. For example, in some cases, we have more defects. In some cases, we have less defects. And in some cases, the defects can cluster together. So how to model that? Murphy proposed to directly use the Poisson's model, e to the power of minus lambda. But instead of using lambda as a constant, Murphy proposed to use lambda as a random variable with some distribution f lambda, and then to use this formula to get the new yield. Here are some examples of the different distribution of f lambda. In Poisson's model, the f lambda is simply a delta function with the constant lambda naught being the average number of defects. So the f lambda can be uniform, it can be triangular, it can be exponential, corresponding to different yields. One thing to mention is that the Poisson's model means the defects, every fabrication, the defects have the same number of defects. So that means among these fabrications, the defects are uniform distributed. But the SIS model is another extreme. It means the defects are more likely to cluster together. So you can use all these models to fit the memory data. There is a lambda naught. That would be one parameter. Here I want to highlight another model that's called negative binomial model. This model is based on f lambda being the gamma distribution. It has one extra parameter alpha. Its alpha is called the cluster parameter. The good thing about this model is that the gamma distribution actually can approximate all these previous distributions with the proper selection of value alpha. That's why alpha is called cluster parameter. When alpha is greater or equal to 10, then this model is very similar to the Poisson's model, meaning the defects are almost evenly distributed. When alpha is 5, it's Murphy's model. When alpha is 1, it's SIS model. It means alpha is 1 means the defects are very clustered together. So the alpha is one characterization of the defect clustering. The thing we care about is actually how to improve the yield. One commonly used yield enhancement technique is redundancy. The simplified scenario of redundancy is that for the chip, it has n identical modules. Among them are redundant. For the chip to work properly, we need to have at least n minus r fault-free modules. So we can actually define m being the number of fault-free modules. So as long as m is greater than n minus r, so we sum over all this probability of m from n minus r to n, that would be the yield. If you use Poisson's model to derive this redundancy model here, the y here, then because each module itself still satisfies the Poisson's model, because Poisson's model assumes all these defects, all these modules are statistically independent. So we can again use the Poisson's probability here to get the new probability. And because this M still satisfies the binomial distribution, we can again use a simple summation to get the new yield. For the negative binomial-based redundancy model, we can use a similar way to derive the expression. We can assume the lambda here is a random variable with a certain distribution f lambda. And when we let the f lambda be in the gamma distribution, we will get the negative binomial-based redundancy model, and its expression is here. So the next is I'm going to show some numerical results. I use one example that's a memory array because this memory array are many modules are identical, so they are perfect example for this redundancy example. This structure is here. It has 512 identical modules. This is derived from part of the bigger memory array in this paper. Here are some results. The first is the yield y versus the average number of defects lambda. So I set the alpha equal to 1.5, meaning there are some kind of clustering of the defects. If you look at when the number is 0, then the yield is 1. That means 100% good chips. When the R equal to 0, this line, blue line, R equal to 0 means there's no redundancy. Then you can see the yield would drop a lot, will drop very quickly when the number of defects increases. But as we increase the number of redundancy from 0 to 1, 2, 3, 4, 5, you can see just a few redundant modules, the yield can improve a lot. The second figure shows the yield versus the cluster parameter alpha. Here I use lambda equal to 5. There are average 5 defects. You remember the alpha, when alpha is 1, it's this model, it means the defects are clustered together. And if you increase the alpha, it means the defects are relatively evenly distributed. You can see among all this distribution of defects, the increase in the redundant modules can improve the yield a lot. So here is a brief summary. Here in this report, I explain some statistical yield models from Poisson to negative binomial, and then explain the redundancy for the yield enhancement, and explain the redundancy model that's derived from the negative binomial model, and finally show some numerical results on the memory array example. And that's it. Thank you.